Hi, so in this video I want to talk about how you can optimize your applications by using caching. And this happens because sometimes we have functions that are called repeatedly during the lifetime of our application. Now if those function calls are expansive, either CPU or memory or latency, and they get called often with the same parameter, then as long as they're invariant, and usually also we insist on something called pure functions, which means they have no side effects either, then we might have the option of caching the results of these calls instead of recomputing the entire call. So there's usually a few things though that we need in order to implement caching, that we need our functions to satisfy. The first thing is that the function should be invariant. And by that I mean that given the same inputs, it will always return the same output. So a function, for example, that is time sensitive because it uses the current time maybe, or uses random numbers. Well, that's not going to work. You can't cache those results because every time you call the function, you could be potentially getting a different result. So that's not going to work, right? So you probably also don't want to cache a function that has side effects. So in fact, you should probably also insist on a pure function, because if you rely on a side effect of your function, maybe to write something to a log or to print something to the standard out, well, if you cache the function, the result is cached, the function will never be called again, right, for that particular set of values, for that particular cache entry, in which case the side effects will never happen again. So this is why usually you want invariant pure functions that you're going to cache. Now, the other thing too is that the function arguments need to be hashable. And that's because of the way Python implements the caching mechanism. And we'll see that in a minute as to why that's the case. Now, of course, it's only useful if the function is repeatedly called with the same value multiple times during the lifetime of our application. And, as long also as the function is expensive to run, maybe in terms of CPU, resource utilization, latency, or something. If it's just a quick function that takes, a fractional microsecond to run every time it's called, do you need to cache it? Yeah, probably not. Okay, so think about that as well. So let's look at how we can implement caching, and I'm going to do it from first principles first so we can understand how caching works in Python, or at least Python's implementation of caching, how that's done. So we're going to use the Fibonacci function, which is going to generate the nth Fibonacci number. So very simple, we're going to use a recursive formula. It's going to say if n is less than or equal to 1, we're going to return 1. And otherwise, we're going to return, well, we're going to take Fibonacci n minus 1 plus the Fibonacci of n minus 2, like so. Okay, so this is our Fibonacci sequence generator. So we could go ahead and generate a sequence. We could say for I in range, let's say 10, and then we will print out the Fibonacci number, so fib I, and then I just want to print it on a single line, so I'll set my end on the print to be this way. And as you can see, we have the Fibonacci numbers. Now let's time this function as n increases. So we're going to say from timeIt, import timeIt, and then I'm just going to say for I in range, and I'm going to start at 25, which is where we start seeing slowdowns happening in the function. So for 25 to 40, of course on my computer, on yours it may very well be different. So we'll time it and we'll basically call Fibonacci at I, okay? So we're going to time that particular call. We'll have to pass it the globals. And we're only going to repeat that one time. So we'll set the number equal to 1. I just want to time one elapsed thing. And then I'm going to go ahead and print and just say f string, and we'll print I, and then we'll just print the elapsed. And then maybe I'll restrict it to 0.2f. Okay, so a float with two digits after the decimal point, like so. So if we do this, and if I fix my print statement, you can see what's happening. It took 0.02 seconds to calculate the Fibonacci for 25, but it's calculating now 37 was 2.59, 38 took 4.2 seconds, and we're still waiting for 3.9 to finish. There we go, just finished, 6.78 seconds. So the problem here is that this is a very simple function to write and to understand, but it is not very good computationally. In fact, this is an exponential increase that we're seeing here. The complexity of this function in particular is 2 to the power of n. So this is a problem, right? So obviously we need to fix this. If our program is going to repeatedly need to calculate 39, 38 or higher numbers, then it's going to be a problem. So we need to speed it up. The most obvious way, and the way we should do it, is to actually rework this algorithm altogether. This is very good for learning recursion. This is a nice example, but in terms of a practical implementation for the Fibonacci sequence, not good. So why is this happening though? Why are we seeing this slowdown? Well, let's go ahead and let's take the same code that I had before. And now instead, we're going to just add this print function. So same as before, I'm just adding this print. And let's go ahead and see what's happening when we call, let's say, the Fibonacci for the 10th element. And you can see what's happening. We have this whole list of calls to the Fibonacci function. 10, 9, 8, 7, 6, 5, 4, 3, 2. Then 2, 3, 2, 4, 3, 2, 2, 5, 4, 3, 2. All these calls, right, that are being made. And you can see how many times the same call is being made to 5, for example, and 5 again. And here we have 5 again, and so on and so on. So obviously the best way is fix the algorithm so it's more efficient. But suppose that we're dealing in with a situation where that's not the case. We can't improve the algorithm. Maybe we're looking up data in a database, or we're making an API call somewhere else, or whatever the case is, but we cannot optimize that algorithm. Or maybe the computational algorithm we have is as optimized as it gets. But we still have problems like this. So one thing that we can do is basically cache the results for each of those calls. And then the next time Fibonacci 5 is requested, instead of recalculating it, just go ahead and grab the cached value. So let's go ahead and do that. And we'll do a very simplistic implementation here, where I'm going to generate or create a dictionary. That's going to be my cache dictionary at the global level. And we're going to define our function. Now I'm going to do just like before. If n is less than or equal to 1, then I'm going to just return 1. Otherwise, what am I going to do? I'm going to check to see if n is in the cache. And if it is, I'm just going to return the cached value for n, like so. Okay? Then I'm going to do my same print as before. So let me go back and pick that up. So let me grab this. So I'm going to print calculating. So if I don't hit the cache, if I have what's called a cache miss, then I'm going to end up at this line of code. So I'll see calculating printed on the output. Now here I'm not going to return the result. I'm going to calculate the result since I have to. It's not in the cache. And before I return the result, I'm going to insert it into the cache. So I'll say cache n equals that. And then I'm going to return the result like so. So now let's see what happens when we do fib10. You can see that we have far fewer calls to the Fibonacci function. Not, unlike what we had over here. We had tons of these other calls. Why? Because we had these cache hits. You could even insert a print statement in here saying cache hit for n, and then you could see that we've had that. So what's the net effect of this? It means that we have a far more time-efficient way now of calculating the Fibonacci sequence. Let's go ahead and time our results again. So I'm just going to grab the same code that we have before. I'll just copy it from the notebook that's available in the GitHub repo linked below. So again, I'm just going to start at 25, end at 39, and then we'll time it just 1 each time. And you can see, okay, I've got the calculating fib. Let me go ahead and just remove that to clean up the display. So there we go. All right, you can see now that the amount of time it took for to calculate number 39 was 1.7 times 10 to the negative 6 seconds. That's a lot more efficient than what we had before, which was 6.78 seconds. So this is how caching can really help us sometimes, depending on the particular use case that we have. okay, we've done it, but there's really a number of problems with how we've done it. It works. I mean, that's fine, I guess, but it's not very good code. It has a number of drawbacks. First of all, this cache here is a global variable. We tend to try and avoid global variables whenever possible. And the caching is kind of baked into the fib function itself. So I had to modify my original Fibonacci function in order to leverage the cache mechanism. That's not good, because that means that if I want to apply the same kind of idea to other functions, I have to modify the implementation of each of those functions as well. So that's far from ideal. And then the other thing too is that we're going to have to create a global cache for every single function that we want to implement this cache for. If I have another function, let's say factorial, well, now I'm going to have the factorial cache, because obviously the cached results for Fibonacci and factorial would be different. So that's not ideal. So instead, what we're going to do, we're going to use closures and, by extension, decorators. Now, for simplicity, I'm only going to handle caching arbitrary functions that use positional arguments only. But the same, kind of idea can be extended to functions that also use keyword-only arguments. So let's go ahead and do this. I'm going to essentially create a decorator. So I'm going to call this decorator cache. It's going to receive its function that it's going to decorate. And now in here, this is where I define the data cache for my cached function. And it's going to be a closure because I'm going to define an inner function, which is going to receive any number of positional arguments. And I'm going to reference data cache in here. So inner is going to be my closure, and it's going to close around this data cache. Now this data cache, this cache function, is going to be applied to different functions, right? Remember, that's what we want, reusability. But which means that when we apply it to different functions, we're calling this with different function argument here, which means this dictionary will be different for every single one. So we don't have now this proliferation of cache dictionaries in our global scope. It's just basically leveraging closures. So we're going to say key equals, I'm going to create a key for my dictionary. How am I going to create a key? Well, I'm just going to take all the positional arguments that were sent to that function that's being cached, right? And I'm going to make a tuple out of that, and I'm going to put that tuple into the data cache. So first of all, I'm going to check to see if key is in the data cache. Well, if it is, I've got a cache hit. And so I'm going to return data cache key, right? I'm going to return that pre-calculated value. Now, if it wasn't, that means I need to calculate it. So now I need to call my decorated function, and I need to pass it wherever arguments were passed in. And now I can go ahead and say data cache key equals result. So now I'm putting the result into the dictionary. And then once I'm done with that, then only do I return the result. And then of course I have to return inner for my decorator to be completed. So you'll notice this is why I need those arguments to be hashable. Remember, I mentioned that right in the beginning, that in the caching mechanism with Python, it works as long as the arguments to the function that you want to cache is hashable. And the reason for it is because we basically just scoop up all the arguments that we use to call the function, put them into a tuple, and then stuff them as the key of a dictionary. Keys have to be hashable, hence why we need hashability here. But essentially, that's the mechanism. So now we can just go ahead and use our original fib function. Remember what it was? It was this one right here. And all I want to do is I want to apply this cache. I do not need to modify now the implementation of the fib function. I basically just say cache, like so. And once we fix our problems, return inner. That's because I spelled it with 3 N's, okay? All right, so now we have our function cached. And it's time to time things again. So let's go ahead and do that. And then you'll see now we get the similar result to what we had when we actually just modified the contents of the Fibonacci function to use the cache. We get the same effect. Okay, so this is how to do caching, very simplistic caching from first principles. But we don't have to implement this cache mechanism ourselves. In fact, the way we just implemented it has some serious limitations. For example, we don't handle caching functions which have keyword-only arguments. Also, our cache size is unlimited. We're not limiting how many items we're going to put into that cache dictionary, which may not be something we want. We may want to only cache a fixed number of values and therefore limit the memory that we're going to use up, right? Because it's this trade-off. Yes, we're getting speed, but we're also trading off more memory usage. At some point, we may want to limit how much memory we want to use for caching. So a common approach here is to limit the cache size. And once the cache goes beyond that limit, we start removing the oldest, or in a particular algorithm, the least recently used items from the cache. So that's called LRU caching. Now there are other cache replacement policies that can be implemented. And if you download the notebook or just go to GitHub, link to that, you'll see I have a link to a Wikipedia page that talks about cache replacement policies. LRU is just one of them and a very, popular one. So Python implements this LRU, this least recently used caching algorithm, in the functools module. So it basically takes care of those two big drawbacks that I mentioned. We don't handle keyword only or named arguments, we don't handle, and we also don't have a limited cache functionality. So from functools, we're going to import LRU cache. Okay, and now let's go ahead and use it with our example. So I'm just going to take the exact same function we had before, but I'm going to apply LRU cache to it, like so. And now our function is cached. We can go ahead and do our timing as well and verify that. And as you can see, indeed, 7.07 times 10 to the negative 7 seconds when n was 39. Now we can easily change the cache size to any specific value. By default, I think currently the default cache size here is 128 elements in here. So that means that we can only cache 128 elements in that cache, and then things are going to start falling off from the cache. Now we can actually change what that value is. We can make it an unlimited cache if we want. We could say it like this, max size. So this is how we specify the cache size. We specify max size in the decorator. If we set it to none, we have an unlimited cache. If we want to have a specific size for the cache other than the default, you just set it. Just say 20, for example, right? So now we have a cache size of 20. We can run our thing again. You can see we still have the same effect. We still have this fast response time. Now for our fib example, if you look at the code closely and the trace outputs that we had earlier, you'll realize that in fact, we only need to ever cache the last two, the most two recently called values. So we could actually limit our LRU cache in this case to 2 elements, and we would not lose the speed benefits. Let's take a look at that. So now we're looking at an LRU cache with a size of 2. And now if I go ahead and rerun the timings, you'll see everything runs just fine. Now, we could go one lower, but that's going to cause problems, right? We're going to have an issue if we go lower. You can see that now we're starting to hit that problem again, because for Fibonacci, remember, we need the last 2 values. We don't need anything else, but we do need the last 2 values. And this is why having a cache size of 1 isn't sufficient, whereas 2 is. So waiting for 39 to finish. Okay, so if we go back to 2, like so, and we're back to that. Now, when we talk about an unbounded LRU cache, there's actually another decorator that we can use instead, which is just syntactic sugar. There is no functional difference from the LRU cache, but it's just called cache. And now you could go ahead and instead of writing this piece of code that we had just now, right, this one over here where we set the max size equals none, you can just replace that and just say cache, like so. Okay, so that will work the same way as an unlimited LRU cache. Now we have to be a little bit careful. There are some finer details and caveats on the LRU cache. And you probably should be aware of those. Let's say that we have a function like this. I'm going to create a different function now. We've got a function of 3 variables, a, b, and c. I'm just going to print the computing a and so on. So let's call it a function. Let's call it with 1, 2, and 3. And you can see that we call the function, this print statement runs, and then it makes the calculation and returns the value. If I call it again, well, same thing's going to happen, right? It's going to basically just run the function again. This is an invariant function. It has, well, no side effects. Actually, it does, right? It has this print side effect. But I don't care about losing the side effect when I cache this function. So now I'm going to cache it. So I'm going to use just the cache. So we'll have an unlimited cache here. And then basically I'm going to just copy this code over here. Like so. And if I call func 1, 2, 3, you'll see that we get computing the result just like before. But now if I call it again, you can see that I no longer get this print output, and that's because it retrieved this value from the cache. So we had a cache hit. Now, in Python, however, you know that you can choose to pass arguments using names as well. I can pass them positionally this way, or I could decide that I want to pass all of them by name. A equals 2, A equals 1, sorry, B equals 2, C equals 3. So from the function standpoint, this call and this call is identical. It's going to receive A, B, and C as 1, 2, and 3. Okay, nothing's changed. From the cache perspective, however, it sees those as a different calling set of arguments to the function. So look what happens. Even though func 1, 2, 3, right, if we rerun it again, you can see there's no print output. We've got a cache hit. When I run this one, we have a cache miss. And so it goes ahead and recalculates, evaluates the function. Now, this is going to be in the cache. So if I call this again, this way, you can see I have a cache hit. I don't get that print. However, if I go ahead and change the order in which I specify those arguments, maybe I'm going to give A equals 1 last, like so, you can see we had a cache miss again. So we incurred the recomputation, right? But now, of course, both ways of calling this function is cached. So I have actually all 3 ways, right? So I can do func 1, 2, 3, you'll see, cache hit. If I do this one over here, then I have a cache hit again. We see we don't get the print. And if I do it this way, we have a cache hit again. As you can see, I don't get the print. Okay, so just something to be aware of when you're using caching. Now, what about class properties? Sometimes we need to apply the same kind of caching principle to properties, and especially calculated properties in our classes. Now, we can do it from first principle, so let's go ahead and do that. I'll just copy paste the code from the notebook. So here we have a circle class. We initialize the radius. I set a private quote-unquote variable radius to whatever that value is, and then I create an area property, which is going to be pi r squared, right? So it's going to take that. So that's my circle class. So I can go ahead and say c equals circle 3. And let's say I want to time now, how much time does it take to calculate that area a certain number of times? So I'm going to time it, let's say, running 1,000,000 times. And you can see it took 0.099 seconds. Is that something I should optimize? Probably not. Am I really going to call on my application the circle 1,000,000 times? Maybe, but if I am, look how much time I wasted on that. It's not that big a deal, right? But depending on your particular case, it may be a big deal. So I'm not saying here that you should definitely try and cache this area property. I'm just saying that if you want to cache a property, here's how you go about doing it. I'm just using this very simple example. So let's go ahead and do this from first principles. So we're going to cache this. So I'm going to set the radius to that. And I'm going to set something called a private, or I'm going to set something called underscore area, which is a pseudo-private variable. Of course, it's by convention private. And I'm going to set it to none initially. And then in my area property, what I'm going to do, and actually, instead of doing this, let me leave this definition here so that we have this and the timing, right? And let me go ahead and create it again, just so we don't lose that timing. So what I've done here is I've set the area to none, right? And then I've created a property called area, just like before. But what I do is I check this private variable. If it's not none, or if it is none, I calculate it, right? If it's not none, I don't do anything. And then I just return whatever that value is. So essentially, I've cached the value for area inside this private variable. And so now, if we redo the same thing here, you can see instead of taking 0.12 seconds, it took 0.076. So you can see that's that speed improvement via the caching. So we don't have to do this ourselves. This is from first principles. It works, but then, we have a much easier way. In Python now, it's something called the cached property, and that's also in the functools module. So let's go ahead and use it. And it's really very simple. We're going to say from functools import cached property, this one, right? Then I'm going to take my original circle class, this one over here, right? And just as before, right, when we looked at how to do LRU caching, or not LRU, but when we looked at how to do caching from first principles, we had to modify, our first example was modifying the implementation of the function to do the caching. Remember that global cache. Here was kind of similar. We had to modify the implementation of the area property in order to leverage caching. Here, I'm not modifying anything. This is the original. But instead of saying property area, I'm going to call this a cached property area. And now we have the cached property. So let's go ahead and do the same timing again. And you can see we now get 0.04 seconds. I don't know if there's any significance to this change here. If maybe their caching mechanism is more efficient than what we did here. Maybe it is, and that's why. But certainly it's more efficient in both cases than this one over here. Now, there is a caveat. There's something you have to be careful about here. This approach here works because our circle class is immutable. By convention, the only thing that I need for the area is the radius. My radius is set to be a private variable. Of course, there's no such thing as private in Python, so if somebody wants to change it, they can. But then, when we use this underscore prefix, and I know if you've listened to my videos before, you know this already. If you're a newcomer, if you see this underscore prefix in a class attribute, don't touch it, right? It's meant to be a variable that's private to that particular class. So this is why I'm saying that this is a private variable, hence I'm not allowing the circle class radius to change. I'm making this class immutable, so it's okay for me to cache the area. Once it gets calculated the first time, I can just keep reusing that cache value because I know the radius hasn't changed, right? But what happens if the radius does change for some reason, right? Let's say that somebody doesn't know this convention or decides that it doesn't apply to them because they're better than convention, right? It's like, the heck with conventions. I'm going to change the radius. So I created my circle, calculate the area, and then I'm going to be clever because I know I can just change the radius directly. It's like, whoever wrote the circle class didn't give me the ability to do so, but haha, I gotcha, I can do that. So I'm changing the radius to 1. I'm happy now, I can go on. And at some point I need to calculate the area of that circle. So I call c.area. And of course, I get the wrong result. Why? Well, the cache hasn't been invalidated. The cache still has the original, value that was calculated when it was first called. Not the new one that should be if the radius was changed. Okay, so that's something you have to be aware of, that this caching, the way we have it here, is only going to work with immutable, with values in here that are not mutable on the class instance. Of course, if you have, some joker who decides that they're going to muck around with your internal variables, well, then the joke's on them, right? But that's not our concern as developers. So how do we deal with this? Because we can deal with it. Let's say we do want our circle class to be mutable, to have a mutable radius. What we need to do, therefore, is keep track of when has the radius changed, and when we detect that it has changed, we need to somehow invalidate this area over here, this cache. So let's do it by first principles first. Let's just see how we would do it if we didn't have this cache property. So we go back to what we were doing before, right? So this is what we had. We've got this area and so on. So this is exactly the code that we had before. Now what I'm going to do is I'm going to actually add a property for radius. So I'm going to create a property. Actually, let me just copy the code so we don't waste time typing stuff. So I'm going to create a property that's going to be both with a reader and a setter, a getter and a setter. Right? So here I read my radius. Here I set my radius. But look at what I do when I set the radius. If the new radius, right, the value that's being passed in is not the same as my current radius, then I need to invalidate the area, set it to none. And then my property doesn't change. The way it implemented that, it checked to see if area was none. And if it was, it recalculated it. So that's going to do exactly what I want. If I change the radius, it's going to set the area to none. It's going to essentially invalidate the cache. And the next time we call area, it's going to have to recalculate the area and then cache it. Okay, so now we can go ahead and do this. We can say c equals circle1. We can look at c.area. We get something that's correct. Now I can change the radius to 2. Okay, and I can look at the c area, and you can see that the area has been updated correctly. And of course, it is still cached, right? So if I was to call the area again, it would come from cache. Let's go ahead and put a print statement here. Print recalculating recalc. Let's just do recalc like so, right? So when I call area the first time, it recalcs. If I call it again, you can see that it doesn't do it, right? It got it from the cache, essentially. If I change my radius and call the area, you can see I get the recalc again. Okay, so this is how we do it from first principles. How about with the Python cache property? Can we do it? And yes, we can. And we do that by actually doing the kind of the same thing. We're going to have to know when the radius changes, right? Because somehow we have to intercept that change to the radius and then inform the cache that, hey, you need to invalidate yourself. How do we do that with a cached property? Remember what we had. That was the implementation. Let me just paste it back here. So this is what we had. So now we're going to have to put in our getter, right? And setter for the radius. So we're essentially going to take this that we had over here. We're going to come back, just paste that in. But we don't have this area over here anymore, right? That's kind of gone. We need to get rid of that. So we've got our getter, we've got our setter. But look at what we have to do here. Before we were invalidating the cache by saying self._area equals none. That's not going to work. We no longer have that. How do we invalidate this? Well, oddly enough, we have to delete the attribute. So we have to delete the attribute from the instance. So it's going to be delete self.area. And then we can set our value. So the interesting thing about cache property is it doesn't quite behave like a regular property. It will basically recreate the property on the fly if it needs to. So if the property area does not exist already on the instance, then it's going to go ahead and create it. And this is how the cache mechanism works, right? Because essentially, when you request it from the instance and area is not there, then the cache property is going to say, oh, I need to create it. The next time when I request it from the instance, it's there. Cache property is just going to sit back and say, no, I'm not doing anything. I'm just going to use the cache, right? So when we do this, we can go ahead and say c equals circle1. And then we can say c.area, okay? And so we get that value. Now, if I change my radius to 2, and then look at the area again, you can see it got recalculated, which is exactly what we wanted, okay? And if we look at, let's say let's look at the dictionary that's currently for that class. You can see that we have the radius and we have the area as an actual attribute on the thing with a specific value. Now, if I set the radius, let's say set c.radius equals 3. Let's look at the class dictionary again. You can see area is gone. It's been deleted. That's exactly what we did here in the setter. And so this means that now when I call area, when I try and get the area, this cache property here is going to intercept that and say, oh, okay, I know that I don't have area in this dictionary anymore. It's not there. Well, the class basically is going to say, the instance is going to say, it's not there. What do I do next? And there's a mechanism whereby cache property can pick up on that and say, oh, okay, you were looking for area. It's not there. I know how to calculate it. I'm going to calculate it and put it into the class instance dictionary. So you can see we get the result back. And if we look at the dictionary again, now area is populated again. So that's how cache property works. And that's how you can invalidate the cache. You just basically remove the attribute from the class instance. Okay, and then the last thing I want to look at is how do we cache class methods? You know, we've seen how to cache properties, right? We've seen how to cache functions using cache and LRU cache, the properties with the cached property. But what about just ordinary methods in classes? Can we cache those? And the answer is, of course, yes, right? But we need to understand that cached property is operating a cache at the instance level. So in the instance itself, cache property is storing this value. So it's using the instance as essentially the way to store the cache data. When we look at using cache or LRU cache on methods in a class, what we're doing is we're actually applying the cache mechanism at the class level, not at the instance level. Okay? So the reason why I'm mentioning this, and most of it is transparent, but the reason I'm mentioning this is that there are a little few things that we need to watch out for. So let's go ahead and let's actually do it. So this time what I'm going to do is I'm going to create that circle class again, but I'm not going to use a property for the area. I'm just going to use a regular method. Okay? And I'm going to cache it. I'm going to use an unbounded LRU cache for this. And of course, again, now we will have to worry about this mutability thing, right? But let's leave that aside for a sec. So now I can create a class, circle1, and I can now call the area method. As you can see, we get calculating area for that. And if I change the radius, c equals r equals 3, and then call the area method again, you can see that we have the wrong result. And that's because, well, this was cached and it doesn't know, again, just like with the property, it doesn't know that the radius changed, that r changed, right? So how are we going to get around that problem? How are we going to fix that? Well, we have to understand something about when our objects, equal, when our instances of the same class equal, and hashability of those classes. So let's go ahead and create two circles. C equals circle with a radius of 1, and C2 equals another circle, also with a radius of 1. Now, C1 and C2 are not the same objects. That's obvious. That's fine. But C1 equal to C2 is also false. And that's because by default, equality is not implemented other than by looking at the hash, right? So if we look at the hash of C1 and we look at the hash of C2, those are two different hashes. Therefore, by default, our equality uses object identity and it says, no, they're not the same. So what we want to do from the cache's perspective though, right? If you think about this cache that we want to do, we really only care about if the radius has changed. So from the cache's perspective, these two circles should be the same, right? If I try and calculate the area for C1 and then calculate the area for C2, well, it should be the same value because they both have the same radius. So what we're going to do is we're going to implement our equality and hash methods for the circle class. And this then will allow the cache, either this one or LRU cache, to understand that, hey, these two items that I'm working with, they're the same, okay? So let's go ahead and do that. So I'm just going to copy paste from the online notebook. And it's basically the same as before, except now we define equality. So we set the equality to be Well, our radius must be the same as the other instance's radius. And then the hash is just going to be the hash of the radius. Okay, just like so. So now we have a class that is a circle class that defines equality based on the value, right? And this value can change. I did not put an underscore in it. I'm not saying it should be private, right? It is public. If somebody wants to change it, they can. And I'm not using a property to control that, right? I could, but here I'm just letting it be a bare attribute. But the cache is still going to know that something's changed. And why? Well, let's go ahead and say circle C1 and C2 equals circle 1. I should say not C1, 1. Okay. So now if we have those two, obviously they're not the same objects. We know that. However, the two are equal. And in fact, they have the same hashes as well. And so when we say C1.area, well, the cache in the circle class, right? The caching that's done at the circle class level is going to see that, okay, you're looking for the instance C1. You're looking for this object C1. Do I have an object in my cache that's equal to C1? The answer is no. So it's going to go ahead and calculate the area for this value of R. Now, if I take C2 and I calculate the area, what's going to happen? Well, again, it's going to go, the cache is going to say, do I have an entry for C2 in my cache? Well, how do I compare objects? By equality, right? When I'm looking for a key in a dictionary, we do equality comparisons. Is C2 equal to anything in the cache? And the answer is yes, it's equal to C1 because we just put C1 in there. So now when we do that, you can see we get a cache hit. We do not miss on the cache. Now, let's mutate the class. Let's say C1.r equals 2, right? And now let's call C1.area. You would think that, oh, you're going to get the wrong answer because we've already cached C1. No, what we've cached is an object whose radius was 1. C1 is now an object whose radius is 2. Do we have that in the cache? No, we don't. So we get a cache miss. And what happened is that that object that we have that was C1 that we stored the result for, well, that is no longer a radius of 1. That's a radius of 2 right now. So if I take C2, which still has the radius of 1, well, that's no longer in the cache. And so we also get a cache miss, right? So just think of that. But of course, now at this point, from this point forward, everything is fine. We can keep calling those things and we get cache hits every time. Okay, so that's it for LRU caching. This is what Python gives us. And there are other methodologies for caching. If the LRU replacement policy isn't what you're looking for, then you'll have to either implement something yourself from first principles, or you can also use third-party libraries which have really done the hard work for you. I put a link to one of those libraries in the notebook that you can download. It's a fairly popular one, and it gives you all kinds of other caching mechanisms, not just the least recently used. All right, thanks for watching.